Right now, returning humans from the International Space Station is the gold standard for spaceflight. It's an incredibly precise operation, but after decades of practice, it has become a familiar routine. When a vehicle like SpaceX's Crew Dragon is ready to come home, it autonomously unhooks from the station and uses a gentle push from its springs and thrusters to drift into independent flight. Then comes the deorbit maneuver. The spacecraft fires its Draco thrusters for several minutes, carefully lowering its orbit and lining up exactly with its designated landing zone back on Earth. Right before hitting the atmosphere at speeds exceeding 17,500 miles per hour, the spacecraft sheds its trunk section, leaving the hardware to burn up harmlessly. At 18,000 feet, 2 drogue parachutes deploy to stabilize the capsule. Once the tumbling stops, 4 main parachutes bloom open, slowing the descent to a gentle drift. Surviving that plunge from low Earth orbit is an engineering marvel. That the physics involved are completely understood, and the entire sequence is a calculable, heavily practiced routine. The Artemis missions present an entirely different problem. Instead of dropping from just above the atmosphere, humans are returning from a dark void 240,000 miles away. By the time the Orion capsule reaches Earth, it is screaming through space at 25,000 miles per hour. That means the capsule is traveling at roughly Mach 32. This chart illustrates the scale of that momentum. Every single kilogram of the Orion spacecraft carries nearly 2,000 times more kinetic energy than a commercial jet in flight. If a capsule attempted a standard steep descent at Mach 32, the resulting friction would generate 5,000 degrees of heat, instantly vaporizing the spacecraft and everyone inside. You can't survive a lunar return simply by building a thicker heat shield. You have to solve an entirely different class of physics. To understand why Orion is moving so fast, we have to look at the launch. Breaking Earth's orbit requires an enormous amount of power, and the Space Launch System provides it, unleashing 8.8 million pounds of thrust. Once in orbit, the rocket's upper stage fires one last time for the translunar injection. This final massive push accelerates the craft to over 24,000 miles per hour, completely breaking the grip of Earth's gravity. This diagram plots the Artemis II free return trajectory. Instead of entering orbit, the crew flies around the moon's far side, using its gravity as a giant natural slingshot. This hurls them perfectly back toward Earth, locked into a homeward path without major engine burns. But all of that accumulated energy has to go somewhere. The sheer speed generated by the rocket's thrust and the moon's gravity must now be entirely absorbed and destroyed by the friction of Earth's atmosphere. About 20 minutes before hitting the atmosphere, the crew ditches the European service module. Because it lacks a heat shield, it breaks away and burns up over the ocean, leaving only the small, sturdy cone of the Orion capsule. At 75 miles up, Orion hits the entry interface, slamming into the thin air so hard the gas cannot move out of the way. Instead, it compresses into a white-hot shockwave, reaching half the temperature of the sun's surface. The heat is so extreme that it strips electrons directly from the air, wrapping Orion in a dense cage of glowing plasma. This sheath blocks every single radio signal entering or leaving the spacecraft. For several agonizing minutes, the crew is cut off from mission control. The ground teams are left in total silence, staring at blank telemetry screens while 4 humans ride a fireball through the sky. The trajectory graph illustrates how Orion manages this entry. By using its shape to generate lift, the capsule bounces off the upper atmosphere like a skipping stone. This lofted approach gives the heat shield time to breathe and vent gases without cracking under immense pressure. Skipping is the only aerodynamic method capable of bleeding off massive deep space energy while keeping G-forces low enough for the people inside to survive. With 4 minutes left, the plasma fire finally dies down. The roar fades into a subsonic whistle, and the voices of the crew crackle back over the radio, but they are still falling at 25,000 feet. To stop the capsule from violently tumbling, the nose cover blows off and 2 small drogue parachutes fire into the slipstream. Moments later, the main event begins. 3 massive orange and white parachutes unfurl in stages, breaking the multi-ton spacecraft down from hundreds of miles per hour to a gentle 20-mile-per-hour drift. Even in the final seconds, calculations are happening. The onboard software automatically adjusts the capsule's roll one last time right before it meets the water. Ensuring it hits the Pacific swells at exactly the right angle is an absolute requirement. Without this final adjustment, the impact shock could severely damage the astronaut's spines. After 20 minutes of sheer physical violence and extreme temperatures, the journey is terminated by a highly calculated, quiet splashdown in the ocean. When you look at the scorched exterior of the Orion capsule, the contrast with the low Earth orbit vehicles from earlier is obvious. The heavy burns tell the story of where it's been. Standard capsules will remain our reliable workhorses for trips to the International Space Station, but Orion is a machine built for a much harsher environment. Getting it safely into the Pacific proves that engineers have successfully solved the massive kinetic energy problem created by traveling far outside our planet's gravitational pull. The atmospheric skip maneuver provides the necessary lift to handle the physics of interplanetary speeds, serving as a requirement for any heavy vehicle returning from deep space. By surviving this 20-minute gauntlet, NASA has established the exact blueprint required to eventually bring humans home safely from millions of miles deeper in the solar system.